Black holes are among the most mysterious and captivating objects in the universe. They represent the ultimate triumph of gravity in regions where space and time themselves are warped beyond recognition. Nothing, not even a photon of light, can escape their grasp. Yet beneath their darkness lies an astonishing truth. Black holes might not last forever. In fact, over incomprehensible timescales, they could slowly destroy themselves, consumed by the very forces that created them. This is the paradox of self-consumption, how the most powerful entities in existence could one day fade into nothingness. Hello 5 Uniques family. Welcome to another video where we dive into the mysteries of the cosmic entities of our universe. The hot seat today is for one of the most enigmatic wonders of the universe, a black hole. Before we begin the video, I would love to know where you are tuning in from today and what aspect about a black hole intrigues you the most. Chapter 1. The nature of a black hole. To understand how black holes might die, we first need to understand how they're born. Every black hole begins with a star, a massive one, often many times the size of our Sun. Throughout its life, the star burns hydrogen into helium in its core, creating a balance between the outward pressure of fusion and the inward pull of gravity. But when the fuel runs out, this balance breaks. Gravity takes over, crushing the star inward. The collapse happens in seconds, forming a core so dense that atoms themselves are torn apart. If the remnant is heavy enough, nothing can stop gravity's pull, and a black hole is born. At its center lies the singularity, a point where matter is crushed into infinite density, and the known laws of physics cease to function. Surrounding it is the event horizon, the boundary that defines the black hole. Beyond this invisible edge, escape is impossible. A black hole, then, is not a solid object. It's a region of space where gravity is so intense that it traps everything, even light. To an outside observer, it appears as a perfect void, a shadow against the fabric of the cosmos. Chapter 2. Anatomy of a Cosmic Beast. Despite their name, black holes are anything but empty. Surrounding many of them is an accretion disk, a swirling ring of gas, dust, and plasma spiraling toward the event horizon. As matter falls inward, it heats up to millions of degrees, shining with blinding intensity across the electromagnetic spectrum. The event horizon marks the point of no return, while beyond it lies the singularity, where space and time themselves collapse. In rotating black holes, an additional layer forms, the ergosphere, where space-time is dragged along by the black hole's spin. Within this region, energy can be extracted through complex processes like the Penrose mechanism. Black holes are not merely cosmic traps, they are engines of immense power. The energy released from their accretion disks and relativistic jets can illuminate entire galaxies. In fact, some of the brightest objects we see in the universe, quasars, are powered by supermassive black holes devouring matter at their centers. Chapter 3. The Appetite of the Abyss. Black holes consume everything that dares to come too close. When a star ventures within reach, tidal forces stretch and tear it apart in a process known as spaghettification. The star's remains spiral into the black hole, heating up and releasing energy as they vanish from existence. Astronomers have observed these events, called tidal disruption events, as sudden bursts of X-rays and ultraviolet light. It's as if the black hole briefly lights up to announce another conquest before returning to silence. For all their destructive power, black holes are not eternal. Deep within their quantum shadows, a subtle process occurs, one that allows energy to leak out. This strange phenomenon is known as Hawking radiation. Chapter 4. The Paradox of Self-Consumption. In 1974, physicist Stephen Hawking proposed that black holes aren't entirely black. According to quantum mechanics, the vacuum of space is teeming with pairs of virtual particles, tiny flickers of matter and antimatter that appear and vanish in an instant. Near the event horizon, these particles can be separated. One particle falls into the black hole, while the other escapes. To an outside observer, it appears as if the black hole is emitting radiation. To conserve energy, the escaping particle takes a small amount of mass from the black hole, causing it to shrink ever so slightly. This process, repeated over unimaginable spans of time, leads to the gradual evaporation of the black hole, a phenomenon known as Hawking radiation. The larger the black hole, the slower the evaporation. A stellar mass black hole might take 10 to the power of 67 years to disappear, but smaller ones, so-called primordial black holes that might have formed just after the Big Bang, could already have evaporated by now. This discovery introduced one of the greatest mysteries in physics, the black hole information paradox. If black holes evaporate and vanish, what happens to all the information they swallowed? According to quantum theory, information cannot be destroyed. Yet if a black hole disappears, that information seems to be lost forever. Physicists have debated this for decades. Some suggest that the information is stored on the event horizon in a kind of cosmic hologram. Others believe it could be released slowly through subtle quantum effects. Still, no one knows for certain. The paradox remains unsolved, a question that strikes at the very foundation of our understanding of the universe. Chapter 5. The Death of a Black Hole. If Hawking radiation continues long enough, a black hole's mass will dwindle. As it loses energy, it becomes smaller and hotter, radiating faster and faster. Eventually, it reaches a critical stage where the process accelerates dramatically. In its final moments, the black hole emits a massive burst of energy, a flash of gamma rays and high-energy particles that could outshine entire galaxies for a brief instant. This would mark the death of a black hole, a final blaze before vanishing completely. What remains afterward is uncertain. Some theories suggest that the explosion leaves behind nothing. Others hint at the possibility of quantum remnants, tiny, stable particles left over from the collapse. There's even a more exotic idea, that the energy released in the final explosion could give birth to a new universe, with its own laws of physics and dimensions of space and time. Chapter 6. The Universe Without Them. Fast forward to the distant future. Stars have long since burned out. Galaxies have faded into darkness. The universe has become a cold, empty expanse, punctuated only by black holes. Over unimaginable timescales, even these final titans will begin to fade. Through Hawking radiation, they will shrink, flicker, and vanish. This period, known as the black hole era, will mark the last active stage of the cosmos. When the final black hole evaporates, the universe will enter the heat death, a state of perfect equilibrium when no energy remains to create change. Time, as we know it, will lose its meaning. The universe will be silent. Black holes are the perfect paradoxes of nature, regions where gravity and quantum mechanics collide. They are born from death, feed on light, and in time die themselves. Through Hawking radiation, they consume their own energy, slowly dissolving into nothingness. In their destruction lies a profound truth about the universe. Even the mightiest forces are temporary. One day, long after humanity is gone and the stars have faded, the final black hole will emit its last whisper of radiation. And in that instant, the universe, vast, empty, and cold, will fall completely silent. The devourer will have finally devoured itself. Until that happens, do not forget to keep looking up at the stars. If you liked the video, do give us a like and subscribe to 5 Uniques for more such content ahead.